Okay, so let's go back to our things. Today, as I told you, we are going to bring all the concepts and things that we saw yesterday to geometry, basically. Okay, so we will see how all the concepts that we saw about topology and the features of NURBS geometry affect the design, affect the final aspect of the geometry we want to design. Okay, so it's going to be, well, not more interesting because I absolutely think that what we discussed yesterday is the basic of everything, but it's going to be more directly connected to your daily practice. So for the moment, I will close Grasshopper because I don't think we will need it initially. Um, and I just wanted to discuss the last topological operation. Well, according to yesterday's let's say sequence of comments, which are the two rebuilds that we have here. Now that we understand what's the features that determine the topology of a curve and how these topology features affect the geometry, we can also better understand the rebuild process. Okay, so for example, um, let's say that we have some kind of curve like this, okay, and for some reason that we are going to explain and why we want to rebuild this curve. Now, rebuilding this curve is something that you do when you want to, well, technically it's called simplify this curve, but simplify doesn't necessarily mean that you are getting to a simpler topology. So simplifying is an operation that we will see also in some dialog window that Rhino uses these simplifying words. Um, but it doesn't necessarily mean that you are going to create a simpler topology with respect to the actual one. So in order to simplify the topology of this curve, because of some modeling needs that we can do several things, but the more immediate and intuitive is rebuilding the curve. Now we have two rebuild commands here. One is called rebuild curve, and one is called rebuild curve non-uniform. Okay. Now, non-uniform. When you read this non-uniform, it's almost intuitive. I don't know if you ever worked with this command, but it's something that has to do with the fact that the topology is going to be non-uniform. Okay, but we also know right now that non-uniform also means that the knot vector is not going to be uniform, which means basically that knots have not a constant step inside the knot vector. So, for example, if we think about a normalized vector for a degree 3 curve, the first value should be 0, 0, 0, which is a full multiplicity knot with parameters set to 0, which is the starting point. And then in a normalized version, you should have 1, 2, 3, 4, x. I don't know how many control points we have in this hypothetical curve. And then the last one, which will be last value, full multiplicity. Okay, this is a uniform knot vector with a constant step, constant separation between the knots values. Okay, but when you create a non-uniform rebuild of a curve, it means also that the step between the knot values is not uniform, is not constant. So basically what you get is that the spans in your curve are not going to be equal and evenly distributed along the path. And so you will have smaller spans, and so you will have knots which are closer and or with less separation, and other parts of the curve where knots are going to be more far apart from each other. And this means that your curve is not a uniform curve. So these are two comments, two different comments. Actually, they both rebuild the curve, so they simplify the curve in terms of topology. So they change the topology of the curve, but they do this, the first one in a uniform way and the second one in a non-uniform way. Now, we are going to discuss the pros and cons of the two. So The first command, it operates a uniform rebuild of your curve. So when you click on this command, it asks for a couple of things. First one, how many control points you have in the rebuilt curve. This is the actual value, okay? And also, if you want to change the degree, I told you that there were commands yesterday. I told you that there were commands that allow to change the degree, and not like a unique operation, which doesn't allow to keep things under control. But inside the rebuild command, you have the degree change here. So you can change the degree inside this rebuild command. And I told you that this is a controlled environment. Now let's try to understand why this is a controlled environment. Okay, so first of all, point count. Let's set it to 10, equal to the actual value, and let's leave 3 as the final degree, exactly like the previous one. So what happens in this case? You see that our curve, despite the fact that we are using the same amount of control points and the same degree, is going to be deformed somehow. See, so the yellow curve is the original one, and the black curve is the rebuilt curve. Okay, why the rebuilt curve has this kind of evident difference or deformation with respect to the original one? Because the rebuild is creating a uniform knot vector. Okay, so it's basically dividing the curve into 7 spans. Okay, so remember that the amount of knot values is set by the number of control points plus the degree, so it's 13 minus 1. So we get to 12, okay? 12 values in the knot vector, considering that the first one and the last one have full multiplicity with degree 3, it means that 6 of those 12 values are taken by the first and the last knot, right? So we still have, so it was 12 minus 6, so we have 6 values inside the knot vector. Okay, so we have the first one plus 6 values plus the last one, so 8 values in total. This means that we have 7 spans along the curve. So you see that everything is perfectly clear right now. So the fact that this rebuild command is creating a uniform knot vector with 7 spans also means that the spans have equal length along this curve. Okay, and therefore, in order to have equal length, the control points that we are considering here are going to be redistributed along the curve. So we still have 10 control points, but having to create a uniform knot vector, the only thing that the command can do is redistribute the control points along the curve. So you see that this maximum deviation appears that says that between the two curves, we have a maximum deviation of almost 1 unit, so 3/4 of a unit. And this maximum deviation is happening in this red dot here. So if we go closer to here, you see that this is the maximum separation that we have between the previous curve and the actual rebuilt curve. Okay. Now, this is something that is not necessarily bad. It depends on what we are designing, at what scale, what does this 0.75 means, because if this is the surface of, I don't know, some stupid example, I don't know, a mouse, for example. If we have a maximum deviation of 3/4 of a millimeter, probably this is not that important, right? But if this is the path of a highway, and we are drawing in kilometers, for example, these are 750 meters of maximum deviation, which basically should mean also that there is some landlord that is going to be pissed off because we are taking away his land. So it depends of what we are drawing, basically. So this is not, this is neither good nor bad. Okay, so you must see if this affects your design in a relevant way or not. Because if this is an acceptable maximum deviation, you just hit OK and you have the final result. Where the final result, I'm not going to delete the input curve. The final result is another curve, which is this one, which more or less has the same shape of the original one, more or less because there was the deformation due to the redistribution of control points along the path. So you can see that the original one had a denser set of control points here, more separation in this area, you see, and then there are these that start to get closer. And then once again, more separation here. But if we take a look at the new one, which is this one, you see that besides the first two control points and the last two control points, more or less along the path, we have a even separation of all the control points. So this is what makes our curve uniform, okay? So the rebuild command creates a uniform rebuild of a curve, while the rebuild curve non-uniform creates a non-uniform rebuild. Now, why should...
Before we go to the non-uniform, just to recap, we made a rebuild, and in this way, we made a uniform span distance, but the span is in between two nodes, if I remember correctly.
Yes.
And once, I mean, our first curve wasn't already uniform in relation with spans, because
yes it was, but yes it was, but the spans in this case, well, we are not we didn't discuss this particular feature. Actually, we are going to discuss this today, but we will be talking about one property of NURBS curve that depends on topology, which is the curve velocity or speed, how do you want to call it. So we are going to discuss also what's the meaning of having a uniform vector, but a different concentration of control points along the path. Okay, so we will get to this point in a while. Okay, so you will understand. You will understand this perfectly. Oh, master curve. This is the right click. Rebuild curves to master curve. This basically sets the topology depending on a master curve. But normally you don't want to do this, because at the end of this analysis of the rebuild commands, I'm going to point out one particular thing with you, because NURBS topology is important when we are going to use curves, for example, in the creation of surfaces. For example, I don't know, probably you have used the sweep to rails many times, right? So the sweep to rails command suggests that the two rails that you are using have the same topology, okay? So in that case, for example, rebuilding a curve to a master curve would mean eventually that you want to rebuild a rail according to the topology of another rail, okay? But we are going to discuss this in a while, because we are going to talk about curve speed. And the message that I want to give you is that rebuilding the curve is not always the best option that you have. Of course, there are situations that we are going to study in which the rebuild curve is the only way you can simplify things or make things more suitable for a regular workflow. But in general, I do prefer to perform direct topological operation instead of rebuilding the curve. So this is the point where we are going to get in a while. And then eventually we will discuss other things, but I think they are less relevant. So this is the rebuild uniform, okay? And the rebuild uniform says, okay, I am going to take the amount of control points that you want, and you're welcome. And I'm going to distribute them in order to have a constant, a uniform vector. Now, one thing is that we place the control point manually, okay? So we exactly know where we want this control point to be, okay? All of them. Another thing is using an automatic command, which is rebuilding a curve, saying only we need 10 control points. So the command, in order to create a NURBS curve with 10 control points and a uniform knot vector, does the only thing that it can do, because there is no preference in placing the control point more in an area with respect to another one. So it distributes the control point along the curve in a uniform way, okay? So it's the only thing that it can do. And then comes the rebuild curve non-uniform. Now, if I rebuild the same curve non-uniform, the thing in this case is that the distribution of spans, or the distribution of control points, which is basically more or less the same thing, happens with a non-uniform criteria, which is based on how much do you want the new curve to be similar to the original one, okay? So an option appears at the command line, which is requested tolerance, okay? So it's different from the other command, because the other command was saying, okay, how many control points do you want? And even this command is saying, how many control points do you want? It asks with a different question, which is max point count, okay? But it's the same thing. Now, it asks for how many control points would you ideally want as a maximum value, and also what tolerance you want me to use when creating the new curve. Now, this tolerance is quite fine because it's 0.1 units, which is 0.1 millimeters, okay? So the curve that the command is creating is basically using 20 control points, okay? And is producing a tolerance of 0.06, which is basically the average tolerance, okay? And you have the maximum deviation, which is always pointed out with this red couple of dots, okay? Now, why this command can be useful if it is producing this kind of irregular topology? Because as it works based on tolerance, it is capable of creating more control point, or placing more control point in the areas where the curve, the rebuilt curve, needs them, and less control point in areas where the new curve doesn't need them. So for example, in this area, where we have more curvature, and also in this area and this area here, you see that the distance, the separation between the black dots is becoming smaller. And even here, it's smaller and smaller, okay? So this is necessary because we set this tolerance to 0.1. So the command tries to distribute the control points along this curve in order to have the less separation possible between the two curves. And in order to do this, as it can create a non-uniform rebuild, it is capable of condensing the control points and therefore the knots in areas with more curvature. So this is a general concept. So I'm going to show you this with with Grasshopper, because it's faster. So I'm going to take a NURBS curve like this, and I'm going to create some smooth area, and then eventually a very, very narrow curvature over there, okay? And I'm going to import this in Grasshopper, and I'm going to divide this curve, and I'm going to divide it with a slider up to 100. So we have a very dense point cloud here if we want, okay? But I want this curve to be rebuilt with less control points, so with less points. So if I connect all these points with a polyline, okay, I get this. Now, if I want the polyline to better approximate my original NURBS curve, you see that with less division point, I get already a good approximation of the smooth areas, right? But as when I get closer to areas with more curvature, you see that we get these kind of cuts here, which are awful, and also they don't approximate very well the original curve. But if I increase the amount of points, you see that in this case, the smooth areas are perfectly represented by the polyline, while here in the area with more curvature, I still have some artifacts, right? So I need to increase this very much. Now think about these points as knots, okay? So you see that you need smaller spans in order to have a better approximation of a curve with more curvature. Now, what the non-uniform rebuild is doing is distributing these red dots here in a more dense flavor here in these areas, and having less red dots along these areas where we don't need them, because it is enough to have, for example, this density in this area, and eventually you need this density here in this little portion of the curve. So this is what the rebuild non-uniform tries to do. Okay, so distributes the knots and control point in an irregular way, a non-uniform way, in order to have the requested tolerance and more or less the amount of control points that we want. So if I set this, for example, to requested tolerance 0.1, maximum point count is set to 30, and it says, okay, I just need 20 points to get to this tolerance, okay? But if I say requested tolerance 0.01, Then it starts to use 28 of the 30 points that I am giving him as the possibility, okay? Because in order to stay that close to the original curve, it needs to distribute more control points and more knots in order to have this kind of tolerance respected, you see? So it is smaller than 0.01. If I say 0.001, then it uses all the 30 points, but there is no guarantee that the actual deviation, you see, is smaller than the requested tolerance, because you see this is 0.001 and this is 0.003 or 0.004 more or less. Okay, so 30 points are not enough to guarantee this kind of tolerance. Then if I say, okay, so use 35, and then we have this value which is higher than this one. So everything is okay. But you see, for example, that these 35 control points or knots, which is basically more or less the same in this case, are being distributed in a non-uniform way. We have several points here and less points in these areas, you see. Okay, so this is the rebuilt non-uniform. I don't want to delete the input, so I'm going to have two curves here, which are more or less identical because of the non-uniform distribution. You see, this is the new curve. Okay, so there are two ways basically. One, which is normally I say in a simplified way that the rebuild non-uniform is based on curvature. So if you want to approximate a curve which has an irregular behavior of a curvature along the path, then you might want to use the non-uniform if you want a more precise rebuild of the curve. Why I don't recommend using the rebuild curve commands in general, okay? Of course, we are going to see in a while that there are situations in which you cannot avoid it, okay? But why I don't recommend to do this in general? Because these two operations here, they affect the whole path of the curve, okay? So let's analyze the two possible scenarios, okay? Two possible scenarios are both, well, the first one is basically concerning the local deformability that we were discussing yesterday. So remember that yesterday when we were discussing the degree change, we were saying, okay, there is the only degree change that makes sense is increasing the degree, because decreasing the degree creates some uncontrolled deformation on the geometry. So assuming we want to increase the degree, we get less local deformation, theoretically, but we also get more control points because the topology increases its complexity, not only the degree. And so we cannot avoid the local deformability by changing only the degree. So for example, let's say what happens when we need the local deformability. So let's go to the example that I was anticipating yesterday. We want to create some ergonomic handle for some device, okay? The average user would eventually also use the interpolate point curve in order to create some curve which is more or less smooth, okay, and does something like this. I'm exaggerating, but you get the point, right? But now that we know topology and how it affects the shape of the curve, we can also do something like this. Okay, I'm going to create a control point curve. I know that I need, well, let's consider the front part of the handle. So we need four areas where the handle is capable of hosting our 4 fingers, right? So what I'm going to do, I'm going to begin this line at the higher level of the surface, which is basically represented by the endpoint and the horizontal tangent direction, okay? Then I need to go down here. And in order to go down here, I will need only 1, 2, and eventually 3 control points. And then once I go down, I also need to raise up once again. And then I need here another 3 control points. And then I need another 3, and then another 3, another 3, another 3. And so we have first finger, mountain, second finger, mountain, third finger, mountain, and we need fourth finger. And we need to raise the surface again and end it somewhere here. So 2 final control points, okay? So we also can create this kind of situation. And once we have it, we can simply select finger, and then there is mountain, and then finger, and then finger, and then finger. And we displace these points down like this. So we are sure that we are getting exactly to the same depth. And here we have the same height. Say this is necessary, I don't know. But we can also use this topology in order to create some nice things. For example, I want this handle to work in a different way or give a global shape, which is different than this flat one. So for example, say I create a reference curve like, I don't know, something like this. And I want my handle to lie on this orientation. So to have this curvature, right? So what I'm going to do, I need here along this curve, I need basically one point which represents this one, another point which represents this one, and then another one, and another one. Okay, so we need 1, 2, 3, 4, 5. Say I want to adapt all this handle here to this line. Okay, so I need 5 reference points, and then I can divide this curve into 4 segments. So 4 spans, 4 segments means I have 5 reference points along the path. Okay, so what I need to do is place the center point of the mountains. Okay, I need to place them along or with correspondences to these 5 points here. Okay, and also the second point here and the side control points here must be aligned with the tangent to this curve in these points here. So I can make some construction lines in this along this curve, like for example going into the line toolbar and taking let's say the tangent from curve. So I want, this is the start line, which is going to be the end point here. So yeah, point. So it's going to be, oh no, yeah. So it's going to be point on curve, like here, and then we have this tangent line, okay? And then I can create another one, point on curve, which is basically also both sides. We can create this line both sides, like, I don't know, something like here. And we are creating this reference line. So once we have them, the only thing that we must do is take these points here and place them accordingly. So I'm going to, oh, I had the snaps disabled. That's why I couldn't get to the perfect or precise points. But anyway, you see that now if I do this, I am creating exactly the geometrical relations that I want for between my handle and this kind of curvature that I defined here. Okay, and because I'm working with topology, I can always take these points and without breaking the rules, the topological rules that I am considering, I can move these points around and have them placed exactly what I want and have the shape that I need here. Of course, I can also take, for example, this line, offset it through points, like in order to have the inner part of the handle, like this, and then use, for example, another division here in order to have 6 in this case. Let me get rid of this. I had the cap activated. So I need to divide this by 5 spans in order to have basically this point for the first finger, this one for the second, this one for the third, and this one for the fourth. Okay, and so on. I mean, you can directly work with topology in order to get to the desired result without having to struggle with interpolated curves or rebuilding lines. Okay, just build the topology you need if you can directly. So this is one scenario. Okay. The other thing that we can do, for example, is this. Okay, I don't want to waste time with the definition of the amount of control points. I just need to take one line, and I need this line to have the possibility of being deformed in order to host 4 fingers and 5 mountains. Okay, so we know that we have 4 fingers means 12 control points. 3 of the 5 mountains means 9 control points. So it is 12 plus 9 is 21, plus 2 plus 2. So 25 control points. I take this one and rebuild it rebuild it uniform with 25 control points and degree 3. So I already have the rebuild curve with the amount of control points that I need. I delete the input because I no longer need the linear curve. And there I have the right amount of points, which are basically this, and then I can take this, and I can take this, and I can take this. And so we already have the right amount of control points and also the perfect distribution, because this is a uniform rebuild, okay? So everything works perfectly smooth in this case. So when you need, for example, a global adjustment of the topology, because you are going to create some kind of extensive deformation along the lines that you are using, then in that case, you might want to use rebuild command. So this is something that you do in order to increase, well, simplify the topology, but increasing its complexity, right? Because you are taking basically into account that if you increase the amount of control points, you are still working with a uniform rebuild. So their distribution along the path is going to be extremely regular, okay? Another situation in which you might want to use the rebuild command is when you have an exaggerated level of complexity of your curves. And this happens with several operations in Rhino. The most common operation that produce a lot of complexity, of topological complexity, are the projections. Projections on surfaces normally produce a very high level of complexity, of topological complexity. So for example, and we are going to start considering some three-dimensional object finally. So I'm going to create a deformable rectangular surface, and I'm going to activate the control points, and I'm going to soft move them in order to create some kind of double curvature aspect of this surface, like here, okay? So we have this double curvature surface, which is this one, and I'm going into the top viewport, and I'm going to create this line. So a very simple line in terms of topology, because it only has 7 control points, right? So what happens if I take this line here? I'm going to move it upward so it is totally visible. And I'm going to project this line onto the surface. So I'm going to use the project command, this line onto this surface. And I get this curve here. Now, from the top viewport, you see that there is absolutely no difference between these two lines, okay? But one curve lies exactly on this surface. So from the front viewport, you see that there is an absolute difference between the two. Now, as this curve must correspond to the original one from the top viewport and must lie exactly on the surface in general, the amount of control point needed in order for this curve to behave like this is enormous. So if I select this curve, I see that if I do this, I have 98 control points along this path, okay? So this is a very high level of complexity, not only because of the 98 curve points, not only for the amount of control points, but also because if you go closer, you will see that in some areas, you have control points which are distributed densely, even very densely in some specific spots, okay? And then suddenly you have this kind of separation, and then this kind, and then this kind. So topological complexity is not only related to the amount of control points you have, but also to the distribution of control points. So this kind of situation here is extremely problematic, okay? Because if you use this curve for whatever type of modeling operation, of surface creation operation, the surface is going to be extremely complex, and eventually is going to behave in a weird way that will affect any other further command that you want to execute on that surface. So we need to get rid.
And there is no way to simplify it.
Yes, there is. This is what we are going to do right now. So
all right,
you have to take into account this complexity here, and you must get rid of this complexity, because else it is going to affect all your workflow. Now, what are the problems in this case? Well, I have a level of complexity here which is so high that the only thing that I can do is rebuild this curve. Now, if I take this curve and rebuild it, you see that I have this amount of control points and this degree, okay? Now, the redistribution of control point always deforms the original curve, right? So in this case, I am decreasing the amount of control points to a quarter of the original amount, okay? 98 to 25. The maximum deviation that I get is almost 1/10 of a unit, 0.09, okay? Now, remember that this is not a problem by itself. It depends on our considerations, okay? So it depends at what scale we are working and so on, right? But in this case, there is a particular consideration. If we projected this curve onto this surface, it means that we want the result to lie on the surface, right? Now, Rhino is saying that along the path, this curve is being deformed, and that the maximum deformation that you get leads to this distance of 0.09, okay? So remember that we have a maximum deviation which is less than 1/10 of a unit, okay? So let's say that I delete the input and say, it's okay. So now I know that I have a simplified version of my original curve, but I also know that this curve has been deformed and that locally it can reach a distance from the surface of a maximum of 1/10 of a unit. Now, if I go here in Rhino units and take a look at the absolute tolerance, I see that Rhino can see details with an absolute tolerance of 0.001. So remember that our curve lies at the distance which is more or less 0.1, okay? So if I ask, for example, if I tell Rhino, okay, I want to use this curve to cut, for example, the underlying surface. This curve cannot be used for that operation because it doesn't lie perfectly on the surface. Where perfectly means that when Rhino projected this curve onto this surface, the result and the amount of control points depends on the absolute tolerance that we are using. So the projection happens considering the absolute tolerance. So the projected curve, the original projected curve, lied on the surface with an absolute tolerance of 0.001, so 1 micron, basically, okay? So it's very precise. But also the projection curve doesn't lie perfectly on the surface. So if we, at some point, decide that we want an absolute tolerance of this, okay, so we increase the module, the absolute value of tolerance, and make Rhino, let's see smaller details. In this case, for example, if we do this after projecting the curve, Rhino will detect that the curve doesn't lie on the surface exactly, okay? So everything is relative here. It depends on the tolerance that we are using. But if we rebuild this curve, for example, we had a maximum deviation of almost 1/10 of a unit, and Rhino is perfectly capable of detecting this separation here, this deformation. And so whatever command you use, Rhino will eventually detect that this curve doesn't lie on this surface, okay? So yes, you can simplify this, but it's not always recommended because it has some side effects. Now, in this case, this is not so relevant because we are working with very small level of details, and because trim operations, for example, are able to cut also in projection. So for example, if I let me split this surface in order to have a surface which is basically totally divided by this this curve. So I'm going to cut a little portion of this surface like this. Okay, like this. So trim can also happen in projection. So if I go into top viewport, I can use this curve to trim the underlying surface. And even if the curve doesn't lie on the surface exactly, Rhino is capable of cutting because we are cutting in projection. So as long as a line visually divides an object into two finite parts, you can use that line to cut the object also in projection, which means that if I take this curve and place it like here, and I go into the top viewport, I can still cut the underlying surface like this, okay, even if they lie at a different height, okay. But this is a particular situation for the trim command, okay. But if we need some more specific operations, that these operations are well, basically should fail due to the absolute tolerance and to the non-perfect coincidence between the curve and the surface. So also, if I take this line, for example, and trim this surface, and go and have a look at the area with the maximum deviation, you see that there is this kind of separation between the curve and the surface. Yeah. So this is what we are talking about. So rebuild in this case, yes, I would say it's necessary because of the topology of this line, of the resulting line from the projection, but you have to deal with the consequences of these operations. Okay, so this is one situation in which rebuild is absolutely useful, and the other one, which is something a little more peculiar, I would say, if I have a line like this one, okay, let me move this thing aside. I have this line, which is basically lies on an horizontal plane, right? So it's perfectly, let's say, visible from the top viewport. And then I go into the front viewport and draw something like this. Okay. Then I have two lines, which can be seen as the two projections of a three-dimensional line, which basically lies somewhere in between, okay, in this area. So we can consider this as the top projection, okay, and this as the front view of one line which lies in this area. So it's like working with orthogonal projection, okay. So there is a command in Rhino which is called curve from two views, which allows to build the curve that has exactly this top view and this front view. So if I select this command here and select this curve as first projection and this one as second projection, I get this line here. Okay. Now this line, if I see it from top, it corresponds exactly to the top viewport, which was the first line that we had. And if I see it from the front viewport, it corresponds exactly to the path of the front view. Okay. So this is the three-dimensional object that corresponds to these two projections. This is absolutely useful when you work, for example, I do always recommend that you start drafting things by hand, sketching by hand. So for example, say you are designing a boat, okay? Then you have the front viewport and the top viewport and the sides, the creases along the hull of the boat, you can draw them like in top viewport by tracing your top viewport sketch, and in the front viewport by tracing your front viewport sketch, okay? And then you can derive the three-dimensional aspect of your curve by using the curve from two views. Now, how does this command work? Well, basically what this command does is this. Take this line here and extrude it like here, and then takes this and extrude it, and then calculates the intersection between these two objects, okay? So between this one, sorry, between this and this, okay? And we have this line. So it's absolutely identical. So once again, we have a line that must lie precisely on these two surfaces, okay? So once again, if we analyze this one, you see that there are lots of control points with a very, let's say, uneven distribution along the path, you see? See how much difference of distribution we have in these areas. And of course, you will have more or less, it's not exactly like this, but more or less you will have more concentration in the areas where the curvature is higher, okay? But this, you see that in this case, the curve is smooth enough. The amount of control points depends mostly on the fact that this curve must lie on two surfaces at the same time, okay? So this is the problem here. So can I work with this curve? No, absolutely not. So even in this case, I want to rebuild it. Now, let's make an intelligent use of rebuild in this case. Okay, so I rebuild this one. And Rhino says, okay, you have 72 control points, okay, and degree 3. And if you use 25 control points, you have a 0.03 zero form, more or less, maximum deviation. Now, my interest is to simplify this topology, not only or not necessarily in terms of the amount of control points, because when I work with this kind of curve, having more control points is not the real problem. The real problem is the uneven distribution of control points along the path. So if I see that 25 control points give me this kind of maximum deviation, and I am perfectly good with this value, I can decide, for example, that I want to reduce the amount of control points, but I also can decide that I want to increase the amount of control points. At this point, the importance is the maximum deviation. There is absolutely no difference in terms of workflow in working with more or less control points. The more important feature here is that we are redistributing the control points. So if I select 40 control points instead of 25, which was already good enough, okay, there is no problem because the distribution of control points is extremely regular in this case. And this is the real problem when working with this kind of lines, okay? So if I want to use this line for some further operations, the fact that I have a regular topology is more important than having a simpler topology. We will see this in a few surface comments that we will going to analyze today, okay? So this is a common use, for example, for the rebuild command, okay? In order to simplify the topology, where simplified doesn't mean reducing the amount of control points or the amount of complexity, but can also mean obtaining a more regular topology, even if with a lot of control points, okay?
Giancarlo, does this command curve from two views work with the non-planar curve?
Actually, no, you have to work with planar curves. But once you understand how the command works, which is basically an intersection between two extrusions, in case you have non-planar curves, you can do two things. For example, let's go back to our original lines, okay, and place them here in an area where we can work, let's say, without being disturbed by other geometry. So, for example, this is something that I always, I also use as a check, okay? So, for example, we know that this command here works with starting with the two planar curves. And the reason why it works with planar curves is that if you have a planar curve, okay, like this one, once Rhino detects that your curve lies on a plane, when you perform some kind of operation like an extrusion, it is capable of automatically selecting the direction of the extrusion, which is perpendicular to the plane that contains your curve, okay? So even if I take this curve and rotate it somehow in space, I don't know, like this, and I hit the extrude command, the extrusion will always come out like perpendicular to the plane that contains the curve, okay? So Rhino needs this in order to create the two extrusions and create the intersection curve, okay? What happens if I take this curve, take one control point and move it up? Okay, I'm exaggerating, okay? This is absolutely clear that this curve is not planar, okay? But let's say that I have a very small variation in the height of this curve, okay? Which is undetectable simply by the human eye. So I have this kind of three-dimensional curve, and I use this command, like with this. Rhino says, okay, la curva, the curve, is not planar. So tell me in which direction you want to extrude it, okay? So once you know how the command works, you also know that there is a way of creating this intersection curve, but you have to do it by hand, basically. You can do it by hand. You can do it by hand inside the command when it asks for curve extrusion direction. So you, for example, go into the front viewport and click like this, and now it knows that you want to extrude this curve in the vertical direction, and then select the second curve. For this, there is no problem because it is a planar curve, okay? And it creates this one. So yes, you can do it. And eventually, you can also bypass this command because extrusion is a very common command, okay? The problem is that when you try to extrude a curve which is non-planar, like this one, Rhino will not extrude it automatically in the right direction. It will take always the positive z direction for the extrusion. Okay, so the fact that this curve is not planar means that if I, for example, rotate it like this, and I expect the extrusion to come out in this direction, if I try to extrude it, as this is a non-planar curve, Rhino will always extrude it vertically, not locally with respect to the plane that contains the curve, because there is no plane that contains this curve, but globally with the z-axis. So, for example, this is important for checking curve planarity. If you extrude something and you see that the extrusion doesn't come out in the right direction or the direction that you are expecting, then it means that the curve is not planar. Okay, so it's an important question, not for the command itself, because the command itself will still work. We'll just ask for the direction of the extrusion. But in that moment, you understand that the curve is not planar, okay? Which is something that you don't want normally. I think there is a question here in the chat. Oh, okay. This is when you want to do the rebuild of a curve, okay? Let's see when you don't want to do the rebuild of the curve, which is the more important part. So, for example, let's say that I got, for some reason, I am modeling something, and then I get this kind of smooth curve. Okay. Remember that all we are saying also affects surfaces. Okay. So we are going to find this also on surfaces. So, for example, let's say that what we want is inside this region here, we want to create some kind of local deformation. Okay. I don't know, toward the inside or the outside of this curve. Okay? Now, local deformability is a thing that depends on the distribution of control points, and therefore also on the distribution of knots, because we know that a set in a degree 3 curve, a set of 4 control points affects the shape of one single span. Okay? Of course, we also know that there is overlapping between the spans. So we know that these 4 control points affect a local span, but also that if I take away this point and consider this one, we have this point is also affecting the same span, which is affected by the previous 3. So there is an overlapping of action between the control points. That's why local deformation is a problem, because if I move this point, I am changing the shape of a whole set of curve, which is a huge amount of curve. Okay, and also if I take this one, I am basically affecting more or less the same area plus a span, an additional span to the left. Okay. So how can we determine local deformability? Well, in order to have local deformability, we need to concentrate control points in one particular area. Now, I've chosen this area because this area doesn't correspond to a higher amount of curvature. So, for example, the higher curvature we have is in this area here, which partially goes into the circle, and in this area here, and also in this little spot here. So I cannot use the rebuild non-uniform, because if I use the rebuild non-uniform, I will get more control point here, more control point here, and more control point here. And in order to have at least a few bunch of control points in this area, I will need to increase the amount of control points too much. So I will get to a non-necessary complexity of this curve just because I want to produce some local deformation in this area. So that's why I do not recommend that you, in general, rebuild the curves. So use rebuild curves only in particular situation where, especially when you want regular topology, okay, not necessarily more control points or less control points, but more regular topology, okay? In this case, what I need to add is more control points in this area. And therefore, what I'm going to do, I'm going to use one of the more important toolbars in Rhino, which is the point edit toolbar. So let's see what we have inside this toolbar, okay? Why do I need more control points? Because the control points are the magnets or are the mean that I have in Rhino to affect the geometry directly. The ideal thing would be to have more spans in this area, right? So more knots in this area. But I don't work with knots, I work with control points. So I need more control points in this area. And also, if I work with control points, I can always use, for example, the 3 rules that we saw about the control points distribution in order to create, for example, tangency, internal tangency, and flat areas, okay? So it is best to have control points in one area. Now, the problem is this one. So normally one would say, okay, nice, I have insert a control point here, so it's perfect. Well, actually it's not perfect, okay? Because this is something that you might want to do if you are in the process of creating a curve or a shape starting from its topology, like we did here. In order to get to this point, I created a straight line, also with a linear equation, with one control point at the start and one control point at the end, and then rebuild the curve with the right amount of control points. If you are into this kind of modeling, then eventually you can also add control points, because when I add control points, remember that control points are magnets. They pull the curve in a particular direction, but they don't belong to the curve. So if I decide, for example, to add a control points along this curve, you see I cannot add control points wherever I want, right? I need to specify some point on the curve. But you see that also, if I move along the curve, the control points lie on the control polygon. So what it means is that if I click here, the control point will lie in this position. So we will have an additional magnet outside from the curve, which will pull the curve out of its original shape. So for example, if I decide to place a control point at this height, like here, you see that the curve is changing its shape in a relevant way, okay? So if I need more control point in this area, what I do normally is pick around here in order to have a more dense distribution of control points, right? And I have this result. Now this result is way too bad, because I have altered the shape of the curve in a dramatic way. And I don't want to do this, because if I do this, the curve is no longer smooth in this area, is no longer smooth in this area. Of course, I can work with control points right now, but I lost the smoothness of the curve around the area where I want to work, okay? So inserting control point is good if you are, for example, in a different situation, like, I don't know, I have this line here, okay? I initially rebuilt it just to have 4 control points and degree 3. Remember that if you want to achieve a specific degree, you need at least that number plus 1 control point. Because if I set this to 3, Rhino automatically decreases the degree to 2, because you cannot create a degree 3 curve with only 3 control points, okay? So we need 4 by 3, okay? And then delete the input. I have a degree 3 control point curve right now, so this is organically deformable, okay? And then I need this curve to deform this curve, for example, in a specific area. In this case, I will use, for example, the insert control point, because I can insert a control point, for example, here and here and here, okay? And so I have 3 control points that I can move along and create the deformation that I want, also being tangent to a particular direction, and also being able to increase or decrease this kind of tangency and so on, right? But this is a different approach, because I have a straight line, okay? So I'm working on topology initially, before then shape. And in this case, I cannot do this. So the best option in this case is to add knots. There is a way of creating knots in Rhino. It's this one, okay? So if I want to create a knot, I can tell Rhino, okay, insert knot. And there is a bunch of points that appear along the path. So you see this one here, and then this one here, this one, and this one, okay? These are the actual knots. So actually, we can see the spans when we try to insert the knots, okay? So knots becomes visible only when you do this kind of operation. Now, we already have a knot here, but this is not useful, because we have a span on the left and a span on the right. I need a span here, okay? So what I'm going to do, I'm going to place an initial knot here, a final knot here, and so I know that inside I have 2 spans already. But I need local deformation, so I need 1 span in this area. And you see that we still have a knot here. So I need to create, for example, a knot here. And you see that in this case, the control points are becoming denser in this area. Okay, you see that this is a control point, this is another one, and let's see if we can detect the next one is this one, which is very close to the curve, and then there is this one, okay? So you can add your knots in this area, and this will create a denser population of control points, which is the side effect, because remember that knots, control points, and degrees are bound by one single equation or formula, okay? So once I have added here a bunch of knots, I go back The curve hasn't changed because the knots are simply topological division, and the control points are adapting to this new topological division. And I have this set of 3 control points in this area, which I can move around, and I get local deformability inside this circle. Okay. And if I want, I can align them, I can rotate them, I can scale them in order to have the same topological control as what we did here with the straight line. Okay. So you might want to work with adding knots and not control points, okay, if you want local deformability. So the thing is that by using this command, or also this one, okay, what we are doing is basically, well, it's still simplifying the curve in somehow, but we are changing the topology in an intelligent way, because we only need complexity in specific areas of our geometry. We don't need to add complexity or to simplify the whole path of our geometry or the whole surface. Okay, so I do recommend that you work with this toolbar before then the global curve tools, which in this case are the rebuild commands. Okay, so try to familiarize with these commands, because these are the key to a smart topological modeling in Rhino. Okay, so insert control point if you are working with a regular geometry, regular shapes, where it doesn't matter more or less if you have some deformation during the point insertion. But in general, I do recommend that you get used to working with knots, inserting knots. Okay, so remember that knots create spans, and spans are driven by a set of 4 control points in general. So once you define little spans here, you are also basically creating a dense population of control points in the correspondent area. And so you have local deformability, right? There is, as we are considering inserting knots in along the path of a curve, we insert knots geometrically, but this also creates a parametric value in our knot vector, of course. Okay, so once we know, for example, that this curve has a domain of 150, for example, we know also that if we insert a knot more or less, I don't know, in this area, it is going to be more or less, I don't know, 100. Okay, so it's 50, 100, 150. Okay, but it's not simply like that. Okay, there is one feature that we were anticipating a few minutes ago, which is curve speed. So you always get a uniform knot vector, but you have to deal with the speed of a curve, which is something that also affects many, it has many consequences, both topological inside when you work inside Rhino, but also in the real world. When you try to fabricate or produce a design, you have to take into account curve speed, especially if you are going to work with CNC milling, for example, okay, where you have a mechanical tool that is moving along the surface of an object. Okay, so in that case, you must consider curve speed. Now, what is curve speed? I will try to explain it like this. I will be using Grasshopper for this, but create a control point curve. Okay, so something which is relevant in order of controlling the speed. Okay, degree 3, which is the default, and I'm going to activate the grid snap in order to draw with some rule. Okay, so I'm going to create a NURBS curve which starts from here, and it has 1, 2, 3, 4, 5 control points, like here in this regular distribution, and then we have another one here and another one here. Okay, and then I create another control point curve here with another control point here, another one here, and then 1, 2, 3, and 4. So exactly the opposite from the other one. Okay. So this is the control point distribution for the two curve, which is basically symmetrical, right? So we have more control points in the first part of the first curve and more control point in the last part of the second curve. Now let's bring these curves into Grasshopper. Grasshopper. Oh, we have some overlapping here, but okay, it's okay. So we have these two curves. I'm going to import them in inside class. Well, sorry, set multiple curves. Okay, we have them here. And what I'm going to do, I'm going to create two ways of creating a point along this surface. The first one is the point on curve, which is a geometrical analysis of a curve, which is based on the geometrical features. So speaking geometrically, these two curves are perfectly identical, right? So I have I can also do something like this. I can also create a straight line from point A to point B, and I can I can do it like this. So I can set multiple curves, like first one, second one, and third one. So the first one is the linear curve, just with one endpoint, the one control point at the start at the end. The second curve has more control point in the first part, and the third one has more control point in the last part. Okay, so I have these three curves here, and you see that Grasshopper is already saying the first one is a line-like curve. Okay, while the second and the third one are linear curve. So the first one is actually a line, but the second and the third are curves that are linear. So it's quite different. So if I go and take a point on curve, you see that point on curve is a geometrical analysis. So it only says, okay, give me the midpoint of these lines. So it doesn't care at all about the topology. Of course, there is different topology between these three lines, okay? But this is a geometrical analysis. So from a geometrical point of view, these three curves are perfectly identical. But topologically, they are very different from each other. So if I take, for example, this point and set it to the start point, okay? And if I go and perform a parametric analysis, like an evaluate curve. Now, evaluate curve is based on parameter. And parameter we saw yesterday, that is that t variable that changes over time and creates the parametric definition of both x and y coordinates of each point of the curve. So as t increases its value, the points that are created of these lines would be the point in sequence from the start point to the end point. So I want to evaluate these curves. We also know that as we don't know the actual domain of these lines, I'm going to reparameterize them in order for Grasshopper to understand that their domain is actually between 0 and 1. So I can use a natural slider between 0 and 1 to evaluate them in some specific point. So if I set the point on curve to mid, I get the midpoint. In the range 0 to 1, the midpoint of these three lines should be 0.5 in terms of parameter value. Okay, but if I set to these to 0.5, I get this. So the first line, as it is a linear line, it has a domain which is actually between 0 and 1, where there is no variation of speed. It has a constant speed because it is linear. Okay, so there is an equivalence between the time flowing and the geometrical spot that we get along the curve. Okay, but if we take into account the second curve, you see that 0.5 parameter corresponds to this value here, to this point here. Why? Because this curve has a denser concentration of control points in the first part. So there is, normally I do this kind of metaphor here, as there are more magnets, the magnets pull the curve like strongly. Okay, so the curve is basically trapped in this area at the initial part. So the point moves slowly in the first part and moves faster in the second part. On the contrary, the third curve has less control point in this area, so the curve is very fast in this area. And so with 0.5, we already reached the second half, where the curve becomes slower. So you see that the distribution of control point affects the speed of a curve. And the speed of the curve is basically the speed of the parameter. So parameters also represent the knots. So if we take a look at this and we go and take the control points command, the control points command, okay, now we have the knots, okay, and these are the control points, the one that you see here. These are the control points. I want to take a look at the knots, okay? So I take a panel and take a look at these knots. So the first curve, it's a linear curve. It only has two knots. The first, which is 0, and the second one, which corresponds to the domain length, which is 60. Okay. The second one has these values here: 0, 0, 0, 15, 30, 45, 60. And the third knot vector also has the same value. So you see that this is the answer to Tiziano's question. You always have a uniform knot vector because this is the standard way in which Rhino creates the curves. Okay, but the speed by which you pass from one span to another span is not constant. It is related to the concentration of control points. Okay, so you see that in this case, for example, if I move these points to the left, let me turn off the point on curve. If I start to move this point, let me enlarge this slider so I can move it with a more fine control. Okay, so if I start to move this, you see that the first curve moves constant. The second curve is slower. The third one is way too fast with respect to the first two. But when I reach a value, for example, of 0.50, I am at the midpoint of the constant speed curve, and I am in the first part of the second curve and the second part of the third curve. When I increase this, you see that the first point moves with a constant speed. The second points tend to accelerate because the density of control point has become lighter. And the third point is moving slower because the curve has more control point in that area. As they have the three curves that have the same domain of 0 to 1, they both reach the endpoints at the same time. Okay, so this is the meaning of having different speeds along the path of a curve. And this is something that also makes you understand what happens when you create, for example, a sweep to rail, and the cross isocurves start to flow with some inclination. Okay, that inclination depends on the speed of the curve, which is represented by the density of control points and the density of knots and spans. Okay, so you always have a normalized distribution of knot values, of parameter values, but it doesn't mean that the length of the span is identical because it depends on the concentration of control points. So time still flows with a constant speed. That's why you have a uniform knot vector also with the same values, okay? But the concentration of control point makes time go slower where you have more control points and faster where you have less control points. So time of 15 for the second curve means something like in this area, while for the third curve means something in this area. Okay, so it is not that the uniform knot vector means physically equally equal length spans along the curve, because we are not talking geometrically, we are talking topologically. Okay, and topologically everything depends on the distribution of control points. Okay, so these points here. Okay, it's quite tricky. It's like thinking about particle physics, about something that you don't see, but it affects the behavior of your geometry. You should think topologically in order to understand this kind of situation here. Because if you still think geometrically, basically you will never understand how you have this uniform knot vector also with same values and have this different behavior along the geometry. Okay, think topologically in order to understand this. But you see, topology is quite tricky sometimes. So let me move these lines here. So yeah, basically what we are doing here is starting to work with topology in the right way, which is creating topological variation only in the area, in the spots where we need them, and exactly how we need them. This is going to make also more sense when we will discuss surfaces, for example. Now, one last thing that I wanted to show you is this one, and then we will switch to surfaces. As we can add knots along a curve, we can also add full multiplicity knots. This is called a kink. Okay, a kink is always a knot, but this is a full multiplicity knot. Now, if you remember what we saw, here, where we were creating the generic NURBS curve starting from the knot vector, we saw that this is a uniform vector, right? But we saw that we can create a full multiplicity knot along the path. Okay, so full multiplicity knot for a degree 3 curve means 3 equal values along the inside the knot vector in the inner part. Okay, so having a full multiplicity knot in the first and last part means that the curve starts from the start point and ends in the end point. Okay, but if we place a full multiplicity knot along the path, what we get is this. One control point becomes a vertex. This is the effect of a full multiplicity knot inside the knot vector. Okay, so Rhino gives us the possibility to insert a kink. So inside the knot vector, we are going to add a knot value, because this is a knot actually, but with full multiplicity. So it repeats 3 times inside the knot vector. And this concentrates, basically, what this thing is doing is concentrating one span in one single point, if you think about it. Okay, so let's bring this back to the original knot vector. So this is a uniform curve. I'm going to bake it, and I'm going to use it for the kink insertion. Okay, so let's get rid of grasshopper for a while. Of course, we can insert knots along this line. If we do this, we can see where the knots are already present. So I'm going to insert a kink in this area, okay? More or less in this flat area. So let's insert a kink on this line. And I did this, preview with the insert knot in order to understand where the actual knots are, because you see that there is no evidence when you insert a kink, okay? So I know that in this area we have no knots. So I click here and hit enter. And nothing changes because we are inserting a knot, okay? So the knot doesn't change the shape of the curve, but it changed its topology. And as this is a full multiplicity knot, it changed it in a very dramatic way that initially is not visible. So let's retake this for a while. Okay, so you see that if we insert a full multiplicity knot, we get a vertex. A vertex is a discontinuity inside this curve, right? So we only have position continuity in this vertex, but there is no tangency continuity. Tangency in this case is discontinuous because in this point, the curve comes from this direction and goes away in this other direction, okay? So we have this kind of tangency discontinuity with correspondence to the full multiplicity knot, okay? And this is exactly what we are doing here. We have created a full multiplicity knot. So there is an internal discontinuity. But as the knots don't change the shape of the curve, which was initially perfectly smooth and continuous, we don't see that discontinuity, okay? There is discontinuity, but it's actually invisible. So inserting a knot is like inserting some level of internal discontinuity, okay? So if I go in 3D and have this curve has an internal discontinuity. If I select it and I activate the control point, okay, you see that where I inserted the knot, I now have this kind of concentration of control points, okay? If I go closer, I also see that this control point doesn't lie on the curve, but this control point lies exactly on the curve, which is something that's completely unusual for control points, right? Because control points normally are magnets that lie outside from the curve. So having this control point lying exactly on the curve tells us that this is the vertex, okay? So think about of this. This is a control point which corresponds to a knot with full multiplicity, and this control point lies on the curve and also creates a vertex. So in this case, our knot created a control point that lies on the curve, which is this one. And if I try, for example, to move it, you see that the vertex becomes visible because these 3 points are no longer aligned, okay? So what's the use of this? Well, actually, we already have it. I mean, this, for example, is a curve which looks perfectly smooth, but it has an internal discontinuity. So if I take this point and move it like this, I have an internal vertex. But this is not actually a polyline or a polycurve. It's just one single curve, okay? So this is very important because we can work with this in a controlled way. So for example, I'm going to undo the insert knot like this, okay? I am back to the original topology of the curve, okay? And I'm going to take this curve and copy it once again to the right, okay? And I'm going to take this one and insert the knot in this area, like here. So what happens, for example, if I take these two lines here and extrude them? So let's start talking about surfaces, okay? And let's see how topology affects also the surfaces in a very direct way. So already in the preview, you might notice that our curve on the right has an additional isocurve exactly in the same point where we inserted the knot along the line. And you see that the surface that's being extruded on the left doesn't have that vertical isocurve, right? So if I confirm this extrusion, you see I get these two surfaces. The only difference between the two is this line here, okay? Now, you know that Rhino, I think Rhino 5 also already introduced the extrusion as a surface type, okay? So we need to explode these two surfaces in order to get to actually to the surface of the extrusion. So I'm going to explode it, and now I have the two surfaces. And so I see that the only difference is still this line here, this isocurve. Now, if we have a full multiplicity knot along the line, we have an internal discontinuity. And if you make the extrusion, you see that that internal discontinuity is generating an isocurve. This is important because now we can understand what are isocurves actually. Isocurves with this level of representation, which is the lowest level of representation for the isocurves, represents the knot lines, okay? So isocurves are isocurves with this level of representation, which means that if you select this surface and go into isocurve density, this is set to 1. So with this density of isocurve, the only isocurves that you see are the knot lines, okay? Not always. I mean, this is a linear extrusion, so it doesn't have any knot inside. But when there is no inner knot, there is at least one isocurve, which is this horizontal one, okay? So when you see this, you still have doubt whether there is an internal knot here at half the height, or this is simply a linear extrusion with a visual isocurve, which doesn't correspond to any internal knot. Now, I know that these are linear extrusions, so I know that this is actually not a knot line, but in general, all these vertical lines represents knot lines. And as this is a knot line, if I activate the control points of this curve, of this surface, you see that I have exactly the same topology here. And as I know that this was a kink, this is also a kink, and this represents a kink line, not only a knot line. This is a knot line with full multiplicity, which is a kink line. So if I take this control point for the surface and this one and move them, what I get is one single surface. This is important, one single surface with an internal crease. This is not an edge, this is a crease, okay? And having one single surface means that I can work topologically in an easier way on this surface, okay? Now I'm going back to this without editing this, surface. I'm going to grab the curve that I already have and copy it once again to the right, okay? And what I'm going to do in this case is taking this point here, this kink, and move it like this. So I get an internal discontinuity, okay? One single open curve, but with an internal discontinuity, okay? And what I'm going to do, I'm going to take this one and extrude it to the same height as this one. Now you see that here we have a bold line, which means that this is not only a kink, this is actually an edge. So if I take this extrusion, open extrusion, and explode it, I have this surface and this surface. So it's different to have a visible internal discontinuity, like in this case, and an invisible internal discontinuity, like in this case here. Because if Rhino detects that discontinuity, it converts it into a physical separation along the extrusion. While if you keep it like hidden, like in this case, you perform the extrusion, the kink converts into a kink line, and you get one single stripe, one single surface that you can work with in a simpler topological workflow. So for example, say you want, I'm going to create the same, more or less the same deformation here. So I'm going to create this one here. So we have basically the same situation, but here we got a poly surface. So I have to join this back again. And here we have one single stripe, one single surface, okay? Which means that if I try, for example, to do something like extracting an isocurve, if I do it on this one, you see that I get discontinuous line, of course, because there is no internal discontinuity. If I do it on this one, I still get one single isocurve, okay? But if I do it on this, Rhino asks for surface for isocurve extraction. So when you have a poly surface, I select the poly surface here. Rhino only considers the first part. And if I want to extract the whole line, I have to repeat the command for this second portion of surface. It also means that if we have one single topology for this complex object, we can also perform some nice complex operations that we will be discussing later after understanding how all the surfaces work, okay? But this is something that also, topology, you see that also affects one very, very extremely simple command like the extrusion, okay? So topologically speaking, there are some differences between adjusting the topology before or after creating the extrusion, okay? Or make let's say, internal discontinuity produced by the kink visible or invisible. It has some consequences when you perform some 3D modeling operation, okay? Kinks are very interesting because as you can see, they work both at the curve level and also at the surface level. And as I told you, the operations that we have been doing with surfaces, with curves, are identical with surfaces. So for example, if I take this surface here, okay, and or this one, which is already a little more complex, and I copy it down like here, and I select it and start inserting, for example, kinks, okay? So I want to insert a kink line along this surface. If I do this, you see that I am inserting an horizontal kink line. If I toggle, I am inserting a vertical kink line. Now, what happens if I insert a vertical kink line? You get the same behavior that we had here. So for example, if I insert a kink line, I don't know, here, and hit enter, I now have an additional line of control points, which are basically the kinks of the curves and the kink line of the surface. So if I do this, I get the same behavior, identical, right? But you also see that vertically, as this comes from a linear extrusion, vertically, I only have one control point here and one control point here, right? So this is a linear extrusion. And moreover, if I take this surface and use, for example, the rebuild surface, which, by the way, is exactly the same command. It depends on what you select as geometry to rebuild. So I can also select the rebuild from the curve toolbar. I get the same rebuild surface, okay? So I don't want to rebuild this surface, actually. I just wanted to show you that in the U direction, which is basically the direction of the profile that we have extruded, we have 18 control points. But in the B direction, we have only 2, which means that the B direction is degree 1, okay? So vertically, our surface has degree 1, okay? So no internal control point, and therefore there is no internal knot. So this is a visual isocurve. It's not actually corresponding to a knot line, okay? But anyway, if I try to insert a kink along this line, not vertically, but toggle horizontally, and I do, for example, this and enter, And now you see that the original isocurve has disappeared because it was only visual. And now we have this isocurve here. This is actually a knot line. And moreover, as we inserted a kink, this is a kink line. If I activate the control point, I get this horizontal line of control points. Now, if I take this point here, for example, well, actually, I'm going to take the whole horizontal set here, and I'm going to move it. So if I move it, the result that I get is this. As the vertical direction of our surface is linear, the internal kink is actually creating a vertex, which is basically creating a polyline if you think about curves. Okay? So if I move this line of kink points, I don't get a smooth deformation of the surface because it is not degree 3, but I get this kind of internal crease, which also corresponds to flat or straight connection between the baseline and the top line. Okay, so I get this kind of weird behavior because of the degree of the surface. Okay, so if I don't want this, if I want to, I don't know, smoothly deform this surface vertically, first what I need to do is take this surface and rebuild it. Okay, but the problem is that in this case I cannot do this because if I rebuild this surface here, not only I will be affecting the V direction, I will also be affecting the U direction. So also if I select 18 control points and I take the minimum amount of control points for the V direction in order to have degree 3, and I don't want to delete the input and hit OK, I get this kind of result. And this kind of result, as it redistributed the control point along the surface, it eliminated the concentration of control points in the kink. So basically, it eliminated the two kinks that I had created. Okay, so if I take the control point, I have this uniform distribution of control points and surface spans, and the kinks, they are just gone. Okay, so if you want to do something like this, like making this kind of kinks along the surface and then having some kind of smooth deformation vertically, you cannot do this sequence of operations. Okay, the way that you do this is like this. Let me get rid of this and let me repeat the extrusion with the pre-existing but invisible kink. Okay, like this. So I have this, I explode it, I have already the kink here visible. Okay, if I work with this extrusion, we know that there is no way of creating a smooth vertical deformation because I cannot rebuild this surface right now. I cannot do it because if I do this, I eliminate the internal kink, right? So what I need to do right now is, oh, well, actually, I can leave this exactly like it was because I'm not going to use it. I don't know why I did this new creation, but I need to do this. Okay. Once I have this surface, I'm going to rebuild it. Let's create another workflow line here. I'm going to rebuild it, and I'm going to rebuild it in order to have 4 control points and degree 3 in the vertical direction. Okay. So I'm going to prepare the surface for this. And how many control points do I select in the U direction? Well, it depends on the deformation that I want to achieve. Okay, it works exactly like with the curve. So I have a maximum deviation, which is actually 1 unit. And if this is too much, which means 1 millimeter, if this is too much, I need to normally increase the amount of control points. Okay, increasing the amount of control points means that the moment I insert a knot or a kink in this area, the deformation that I can get will be eventually more local than this one. Okay, so I need to consider this. So let's say that 18 is perfectly fine, and this 9 spans is okay, and this kind of deformation is okay. I simply hit OK. I want to delete the original. Well, I don't want to delete the original surface, so I'm getting this new one here, which looks smoother, by the way, because of the redistribution of control points. You can see that control points here are more evenly distributed along the path. Okay, and we have increased the amount of control points. Okay? So once we have these, we go and insert the kink line on the surface, not horizontally, but vertically, like here. So we can create the kink lines. You see that now all the vertical lines have 4 control points because we have already changed the degree of our surface. We can create this this kink deformation here, but we can also create now internal kinks horizontally. And as this is a degree 3 interpolation in the vertical direction, we will also have some kind of organic deformation. Oh, by the way, we have 4 control points and actually one visible horizontal isogroup. This is still a visual isogroup. This is not an internal knot, okay? Because with 4 control points and degree 3, we get one span curve. But now if I insert a kink line, like enter, you see that now we have an isocurve here. The original one disappeared because it was just visual, and we get only this one, which is exactly what we were getting by inserting the knot here or here, okay? But this time things works differently, because if I select all these control point line, for example, I want to create some kind of kink deformation in this area, okay? So some complex modeling occurring here. So let's say that this is, for example, the inner part of a wardrobe, and I want to add a seat in this area, okay? So I create this kink line, and I take these 3 control points here, move them inside, and I am creating this kind of, let's see it with shaded, creating this kind of situation here. The kink becomes visible only where you displace the control points. And so if I want to concentrate this kink in order to make it look like a seat, I don't care about the lower part, but I need this part to be more flat and horizontal, right? So what I can do, I can take these control points in this area, which determines the tangency starting from the kink up. So I can take these 3 control points, 1, 2, and 3, and bring it down like this to the horizontal, more or less. So I'm setting this tangent like horizontal. You see that the surface is already reacting to this. And also what I can do, if I don't want to go out from Rhino in my workflow, I can also go and change the weight of these control points. So I can increase this, and I can see how the surface starts to react to this deformation and start to create this kind of nice, smooth behavior for my surface, right? So you can do whatever you want with point editing once you know how this operation works, right? So there is no need, or well, more or less, there is no need of creating extremely complex topologies if you don't need them. You can create local deformability by adjusting the topology the right way. By the way, working with point weight is not let's say, recommendable in general, because the deformation that you get on surfaces, especially when you have kinks, it's less controllable than when you work with more smooth surfaces. For example, the fact that this weight is increasing here not only is pulling the surface down, but it's also pulling the surface towards the point from the side. Okay, so you see that there is this kind of torsion here, and this kind of kink is being visible also on the other side of the surface. So eventually, in this case, instead of increasing the weight, I would introduce some knot lines in order to have more control points in this area. So for example, I would create a knot line, not a kink line, but a knot line along this surface horizontally, which means basically in the area where I want to adjust the upper surface of the bench. So I would take here a few knots like this. So I have more control points in this area, and this is naturally starting to pull the curve down. And if I, for example, take these control points in this area, like these 3 here, and move them toward the outside, now I am creating the flat part without disturbing the rest of our surface. Okay, so everything here is being conducted directly with direct topological editing. One last thing, and then I will check the chat. Sorry. The fact that we are changing the topology in one specific area is not like with the curves. So with curves, you can, I don't know, insert control point in only in the specific spot when you want to produce some kind of local deformation, okay? And this is not affecting the rest of the curve because you are working with a linear object. But a surface in Rhino is something like this. Now, NURBS surfaces are mathematical objects where you have this kind of, let's say, rectangular behavior. Okay, so all Rhino surfaces have rectangular topology, which means that if you do something in a specific area, this something will propagate along the surface both horizontally and vertically. Okay, so if I need, for example, more control point in this area, in this spot, I will have more control point along this direction and along this direction. Okay, so I am inserting lines of complexity, and these lines propagate all over and all along the surface. Okay, so having inserted control points, kink points, and etc. in this area also affected the presence of more kinks and more control points along the surface at the same height. Okay, this is because Rhino works with the NURBS object. If Rhino worked with T-splines, for example, which is not a software, T-splines is a type of geometry. In that case, T-splines means that at some point, for example, let's say that you have a surface like extending upward like this. Having T-splines means that at some point, your topology can do something like this. So that's why it's called T-splines. You can have branching and different distribution of the topology at different steps, at different level along your surfaces. Okay, but this is something that eventually is handled by software with a different type, different approach, which goes through mesh objects normally. Okay, so this is the difference between NURBS and T-splines. Whatever you do inside your surfaces will propagate horizontally and or vertically. Okay, let me see what's the question. So in general, to create creases on surfaces, we work with kinks directly on the surfaces instead of creating the kinks on the curves that we generate the surface. Exactly, because if you visually create kinks on the curves, then you will get polysurfaces. Okay, and this is also this is a convenient workflow, because if you have one single surface like this, you can do whatever you want on the surface. You can also apply, for example, a pattern on this surface in a very easy way, because you only have one surface and not a polysurface. Okay, so it's absolutely convenient to create eventually invisible kinks in area where you want some crease happening, and eventually deform the shape after having creating the internal discontinuity. Okay, so keep it invisible actually. And creases are also very nice, let's say, techniques to create some interesting shapes. For example, now we were working with extrusion, but I will not concentrate on extrusion because it's very easy to work with it, but it's important to understand how kinks work and internal discontinuities work with a simple command like this. But once we know how it works, we can take advantage of this particular behavior in very complex surface modeling. So for example, where complex surface modeling doesn't mean that you necessarily have to use complex surface creation tools, okay? So I normally recommend that between all the surface creation tools, you try to use the simplest ones. And the simplest between all of these surface creation methods is using the loft. The loft is an extremely powerful tool. Okay, so I do recommend that when you need to create some complex geometry, some complex surface, first check if you can do it using a loft, because the loft gives you, I mean, the perfect balance between complexity control, geometrical control. So you normally should get the simplest possible result, also with very complex geometries. So for example, let's say we want to create a flat surface with some internal crease that simply fades towards the edges, okay? So if I take, for example, two simple lines like this and this, and I create a loft between these two lines, as this is a loft between two cross sections, there is nothing that tells this loft to create some internal deformations, right? So if I create a normal loft without simplifying. You see, simplifying. Okay, it's not necessarily simplifying the cross section. It means changing the topology. Okay, so if I don't touch anything here and I hit OK and take this surface and activate the control points, you see that even if I am creating a straight loft between two straight lines, I get a degree 3 surface in the longitudinal direction, while in the cross direction, the loft respects the topology of the curves that we are using, which is basically a linear curve. So degree 1, so one control point here and one control point here. But the flowing on the surface also through two simple cross section happens with degree 3. So this surface is already deformable internally in the cross direction with a degree 3 deformation, so organic deformation. Okay. But what I cannot do in this case, for example, well, the only crease that I can create in this case is adding a kink along this surface in this direction, like here, for example, and I have this kink line that is capable of creating this crease like this. Okay. But if I want to create something more complex, okay, so I'm going to just take the two lines and copy them here. Let's move all of these to right, okay, and move it like here. Okay, so what I want to do right now is consider an internal cross section. This internal cross section, I'm going to create it like with a control point curve, like from here to here to here to here. Okay, so perpendicular to the two longitudinal edges, okay, with 4 control points, which will allow a degree 3 interpolation in the cross direction. Okay, so I'm not going to use this, of course. I'm just lofting this with this with this. Okay, so of course now the loft has to deal with two different complexities for the cross section curves. Okay. What complexity will have the loft surface by using these 3 curves? Well, it might already be clearly understandable, but let's specify this. Okay, we have a complex topology, let's call it complex, and a simple topology for the first and last cross section. Okay, so we have a degree 1 with 2 control points, degree 3 with 4 control points, and once again degree 1 with 2 control points. What features, what characteristics must the loft surface have in order to respect these 3 type of cross section? It must have the topological complexity that allows to represent the more complex cross section. So think about it. If the loft would adopt the simple topology like this one, so 2 control points, it wouldn't be capable of deforming like this. Because in order to get an organic deformation, you need at least 4 control points and degree 3. While if the loft adopts the 4 control points degree 3 topology, it can align the 4 control points like this and reproduce the linear aspect of this cross section. So the internal topological complexity of a surface depends absolutely and totally from the topological complexity of the cross-section curves or the construction curves that you are going to use. Okay, so if I don't do anything here and hit OK, I get this surface, but this surface has this topology here. So there are 4 control points, well, actually 5 control points in the longitudinal direction and 4 control points in the cross direction. Why 5 control points in the longitudinal direction? Because there is an internal, you see, this surface has an internal isocurve in this situation. Remember that when the loft was created only using the first and last cross section, it was already creating a degree 3 interpolation. Okay, so if I take this surface here, okay, and I, for example, try to rebuild it, and I use the same amount of control points and the same degree, you see that we have span counts in the U direction, which is the red arrow. We have 2 spans. It already has 2 spans, so that's why we have 5 control points. Okay, so we have this isocurve here is a real isocurve, while this one is a visual isocurve. Okay, because our surface has a 4 control point topology in the cross direction. Okay, so if I have this surface here with this topology, and I try to add, for example, a crease with a kink line, now the kink line is going to deform because it is a degree 3 curve. Okay, so if I place a kink line, for example, at this level and at this level here, okay, and I activate the control points of this surface, I have this situation. Now, the kink line is recognizable because it reaches the isocurve in the end point. Okay, so I understand that this is a kink point while this is not. Okay, so I take this one and this one and this one and this one, sorry, this, and I can produce this kind of kink, which is an organic kink along the surface. But also what I can do is take only the internal kink point and increase their height and create this kind of internal crease that disappears when it reaches the edges. I can also do something like more interesting. For example, I can take the original surface, I can insert knot lines and not kink lines in this surface in the longitudinal direction, like very close to the edges, okay, like this and this, okay? So when I activate the control points, I can create, for example, taking the crease point with the knot, the kink point, sorry, which are these two here, and also eventually these two here on the other side of the surface, and eventually increase their height. And I am basically concentrating the crease in the inner part. And as this kink point is still lying on the floor, there is horizontal tangency. So the crease is disappearing more gently when it reaches the edge. Okay, so I can create very, very nice smooth surfaces with internal creases without working with polysurfaces. Okay, this is something absolutely fantastic if you want to create very complex shapes. For example, if we are considering this on the plane, and of course, I'm just increasing the height of these points, but I can do also some more dramatic deformations. Like I can take, well, not all at the same time, but I can take these points here and do something like this. And eventually after I can move this crease along the side, and I can do the same to these points, move it up, and then move it aside on the opposite side. So I'm creating this kind of wavy behavior, which is something like resembles me to some, I don't know, tensor structures or something like this, you know, something that is being pulled, some soft body being pulled from these kink points. Okay, but anyway, this is something that opens this very complex topological modeling. Is created by a direct control of the topology, be it control points or knot lines or kink lines. Okay, so it's very nice to work with these techniques because it gives you access to this kind of complexity, but with a very, very simple topology. Okay, and
so
also, yeah, tell me.
Basically, these two knots line that you generate makes the last part smoother because they create 4 control points in the last part. Is it correct?
You mean this knot line
yes,
here?
Yes.
Okay.
Yes.
Look, well, actually, I need this not for smoothness control, but to determine when the crease is going to disappear towards the edges. So, for example, if I undo these edges, this knot line, and I repeat them, and I create more in towards the inside, like here, and activate the control points. Now, basically what I get is that if I take the inner control points here, and also this one and this one, I can still produce creases, but these creases tend to die sooner than the previous case, okay? Because my control points are more separated from the correspondent edges. So basically what I'm doing with by adding this knot line is creating this line of control point here, and also this line of control point here. Okay, so the thing is that if I create the knot line more on the inside or on the outside, basically the effect is by having this point here more or less towards the center part or toward the edges. And if I move them towards the center part, I get a more localized crease on the inner part of the surface, which dies gently towards the edges, okay, as you can see here. So we can play around with this thing in order to have the right distribution and shape of our creases along the shape of the surface, okay? And this is important, this is interesting, because if you work like this, you are at the same time performing a geometric editing and also a topological editing, okay? And this is important because if you have a topology that corresponds exactly to the shape of the surface, whatever type of additional modeling workflow you want to adopt, it will be smoother and easier. For example, let's say you want to create some kind of stripes, okay, in this area. As the topology corresponds to the shape, you simply have to, I don't know, extract some isocurve in the right direction, which is this one, and start creating, for example, these isocurves like this, okay, and eventually limit these stripes to a specific area like this, which is also possible because of the control topology, and use these curves, for example, to create some cuts along this surface. Okay, so we are creating some kind of um, um, what's the name of this thing? Uh, I don't remember, but anyway, we are creating this kind of control design on the sides of this slope here because the topology is absolutely under control, okay, and corresponds to the shape of the object. So it's very nice to work with topology because you can create these kind of complex things with very reduced effort